right, let's look at some practice problems. All right, in this practice problem, we have this difference equation, and we have this candidate Lyapunov function, x transpose px of t. So this is our P matrix that we're looking at, and you can go through and show that in fact that matrix is positive definite. Again, one way to check for positive definiteness is to check the eigenvalues of a matrix. Okay, so check the eigenvalues of a matrix. And so another way, if it's a 2 by 2, then it's really simple. You check the diagonal elements to see if they're all positive. Then you check the determinant of the matrix. And so you could go through and show that the determinant here is going to be positive. So if both of those things are true, then the matrix is positive definite. Okay. To determine now whether this is a candidate Lyapunov function. It's not a real Lyapunov function until you've actually proven it. So here's our candidate, and we put it through its paces. So delta of v of x of t. So this is v of x of t plus 1, v of x of t. So I'm subtracting the two. But v of x of t plus 1, x of t plus 1 transpose is equal to x transpose a transpose. X of t plus 1 is ax. Here I have x transpose x. I can factor out x transpose on the left, x on the right, and I get this quantity. Okay, and so now I need to check this quantity to see the definiteness of this. It needs to be negative definite. So if I form Q as minus this quantity, then Q needs to be positive definite. So we form this quantity, A transpose PA. So we were given A and P. We plug them in here. So here's A transpose. Here's A transpose PA. Here's P. Subtracting the two, we get this matrix, which is clearly positive definite. Again, how do you check it's positive definite? You check to see if the diagonal elements are positive and if the determinant is positive. In this case, the determinant is 2, so it's definitely positive. For a diagonal matrix, it's even easier. All you have to do is check to see if the diagonal elements are positive, because the determinant will be the product of the diagonal elements. If they're all positive, then the product will be positive. So if you actually went back and checked the matrix A and checked the eigenvalues, you'd find that both of the eigenvalues are at 0. So clearly this matrix is stable. That is, the eigenvalues are inside the unit circle. So that's the stability for a discrete time system. Here we have a continuous time system. And so here's our A matrix. X dot is equal to AX. We're going to start with a Q matrix that's the identity matrix. And now we want to find P that solves the Lyapunov equation. So here we're going to do this the brute force method, where we let P be a symbolic matrix. We multiply this out, A transpose P, and then add P times A, and then add Q, and this is what we get in terms of those unknown quantities. We can go through and solve this set of equations for the values for P11, P12, P21. I'm not seeing P21 in here. Oh, it's symmetric, so these guys are the same. P21 is equal to P12, duh, and then P22. So when we go through and solve this, we actually get, even though it looks like 4 equations, these 2 equations will always be the same, again, because all of this is symmetric. And so we actually only have 3 equations, we have 3 unknowns, we solve them. So this one, for example, is easy to see. P12 is going to be, in order to make this 0, P12 has got to be equal to 1/4, so we've already solved for half of the unknowns. So P12, and then I can plug that P12 in here and solve for P22. I get 1/4. And once I have P22, I can plug it in here and solve for P11, and I can get 5/4. Again, the diagonal elements are positive. the determinant of this matrix is 1/4, which is positive, so P is a positive definite matrix. All right, so given a system that's like this, x dot is equal to ax, with this candidate Lyapunov function, x transpose px. Okay, now here we've chosen P to be the identity matrix, and A is this matrix. It's a symbolic matrix, but notice it's not completely random. I have these two that are the same, and these two are negatives of each other. So when I form Q, which is minus A transpose P plus PA, I get this matrix, which is equal to 2 times A times the identity matrix. And so this matrix Q will be positive definite as long as A is positive. If we went back and checked the eigenvalues of this matrix, we would find that in fact they're at minus A plus or minus JB. So notice that the real part is what determines the stability, and notice that as long as A is positive, then this eigenvalue will have negative real part. So we can actually prove that directly using the Lyapunov function, which it's kind of a lot of work to do that, but you know it can work. So consider now this should say x dot. The Lyapunov function, x dot is equal to ax, the system, Lyapunov function, x transpose px, we're going to consider this for A, and P being this. For P to be positive definite, we need to have this positive, and the determinant positive. And so here's the determinant being positive. It means this. The product of these two is greater than the product of these two. So we're going to choose as a candidate or as a Q, we're going to choose this and solve for P. Okay, so when we do that, we get this set of equations. Notice again, these two equations are identical. We can put these two into a matrix equation, these three equations into a matrix equation. So here, this equation becomes this first row, this equation becomes this second row, and this third equation becomes this third row. And so we can solve now this equation for P, and when we do, this is what we get. And it's like, wow, that's kind of messy. How do we check what's going on here? Well, again, we need these two guys to be positive, and we need the determinant to be positive. Okay, so what about the determinant being positive? Well, this numerator clearly is going to be positive because this is non-negative, and this quantity is non-negative, and then this stuff is non-negative, and so P will be positive definite as long as A0 is positive. Okay, so everything here is positive except possibly this, so this whole thing will be positive as long as that's positive. Okay, and in fact, if this is positive, then this quantity is greater than 1, and so all of this is going to be a positive number. Okay, so that's something that we need to have. So A0 needs to be positive. In order for this element to be positive, if A0 is positive, I need to have A1 be positive. So this tells us what we need to have for our system to be positive definite. So for this controllable canonical form to be stable, I need these guys to all be negatives, or so negative. So this is positive, so that negative is negative, and so that's what I need. That's what this is telling me. So if I've got this equation, so in this case, notice that these are both negatives, or that is the coefficients A0 and A1 are both positive, then we can go through the paces and find out, in fact, that this gives us a P, that's this matrix, and we can go through and show that that is in fact positive. Now in this case, the Q is obviously positive definite, so we're good here. All right. Here is this matrix and this Q. Let's check on bounds for the solution of these equations. So notice that the minimum eigenvalue for Q is 1. The maximum eigenvalue for P. So the P here, if we compute the eigenvalues of that matrix, the maximum value will be this. Okay. So if we look at this quantity, the minimum of Q divided by the maximum of P, we get this ratio. And which is basically just the inverse of this, which is this. And so we can prove that our system is asymptotically stable, actually exponentially stable, and the system decays faster than this exponent. That is, the state, the norm of the state itself will decay to 0 faster than this exponent. So, generally speaking, this formula that's given here is actually conservative. That is, in general, the system itself the state will decay a lot faster than this exponent, this exponential. All right, what about a nonlinear system? So we consider this nonlinear system. This is called a van der Pol oscillator. If we consider this nonlinear system and evaluate it at the origin, okay, so we let the origin be the equilibrium condition, which in this case it actually turns out to be an equilibrium condition. So when we take the partial of this system f with respect to x, we can go through and show and if we evaluate it at the equilibrium condition, we can go through and show that this is the A matrix we get. If we compute the eigenvalues of this system, this is the characteristic polynomial we'll get. This has eigenvalues here which have negative real parts. This has eigenvalues. There should be a j here. Yeah, these have negative real parts. There should be a j in here. So again, looking at this system, if you want to solve this system using Kronecker products, then I would perform this Kronecker product. So remember, I take each element of this and multiply by this matrix. So A transpose is this matrix transposed, and so I have 1 times this matrix, and then I would have 0 times this matrix, that's this, 0 times the matrix transpose, 1 times the matrix transpose. So that's this quantity. And then I have this matrix transpose times the identity. So I have 0 times the identity. This matrix transpose, this quantity times the identity, this quantity times the identity, and then this times the identity. So that is the Kronecker products. I add them together, I get this matrix. So computing the inverse then, I get this vector, and that gives me this solution P. So we can go through and directly compute solutions. We don't have to do it in symbolic form. We can actually form a matrix equation that we can then solve to give. So this quantity here is actually this matrix inverse. We can then solve the equation to give us the vectorization of P. And in this case, P is a 2 by 2 matrix. So it has columns of 2. So this column and this column. So this column goes up over here, and so that's how we unvec the P, the vectorization of P. So this is Lyapunov stability.